Good morning to one and all present here. It brings us immense pleasure to present our poster on improving accuracy of peak power estimation of digital circuits using ATPG-based techniques, authored by myself, Shakti Shrey, my colleague Arushi Vashudevan, and our mentor, Dr. Sneh Saurabh sir from IIIT Delhi. So while optimizing the circuit to achieve better performance, it is essential to realize that the increase in performance doesn't come for free, and rather we need to negotiate the power performance trade-off such that the system resource utilization fits in our power budget at the given operating conditions. Thus, it becomes necessary to know about accurate estimate of power consumption at right time in the design cycle. Even though the post layout calculations are more precise, the estimates are available late in the design cycle. In contrast, the RTL power estimates available early in the design cycle are significant to assist the design teams in finding power bugs at the very early stage of the design. However, the challenge around accurate estimation of power in digital circuits can be understood with the help of these two RTLs implementing similar functionality here in the preface section of the poster. Which RTL do you think is better modeled for power? Is it RTL1 or RTL2? What do you think? So it turns out that the nature of input signals, that is toggling of ABCD or toggling of CS, will decide which RTL is better modeled for power. If toggling of inputs ABCD is more compared to toggling of CS, you can observe that the stimuli triggers more activity in RTL2 compared to RTL1, and thus in this case, RTL1 consumes less power. In contrast, if toggling of inputs ABCD is less compared to toggling of CS, the stimuli generates more activity in RTL1 compared to RTL2, and hence RTL2 is better modeled to operate at low power in this scenario. Thus, it is very important to realize that the essential information required for accurate dynamic power measurement at given operating conditions is the knowledge of real-world stimuli based upon the actual use case scenarios of the design, as well as understanding and analysis of different nets and gates which will be switching in the design across those different sets of use case scenarios. Moving further, to study the impact of input stimuli and its coverage on power estimates, we started to analyze the impact on power estimates due to test stimuli targeted in verification process to maximize the functional coverage. We used constrained random feature of system verilog to generate test vectors where we gradually relax the constraints on inputs using pickle scripts to generate sets of input vectors associated with gradually increasing coverage numbers. These test stimuli with gradually increasing functional coverage are used to perform RTL simulation in order to generate VCD files and corresponding coverage reports using Cadence NC-SIM tool, and correspondingly using Synopsys VCS, the generated VCD files are converted into the SAIF files, which are used to annotate the switching activity on gate level netlist obtained from logic synthesis of RTL using Synopsys DC compiler in order to generate power reports with the help of Synopsys power compiler corresponding to the sets of input stimuli with gradually increasing functional coverage. We observed that even for low functional coverage of input stimulus, the power estimates are higher compared to power estimates corresponding to stimuli with high functional coverage reports, and vice versa. Further, in-depth analysis of activities at different nets and gates in the design suggests that the high power number is heavily influenced by toggling of some of the large fan-out nets in the design. Thus, our proposed method of peak power estimation technique revolves around prioritizing the toggling of heuristically selected large fan-out target nets in the design and determination of corresponding input test vectors using ATPG and intelligent pattern compaction techniques, which reflects better peak power of the design.
So coming to our proposed ATPG-based peak power estimation, we have used the following tools. First, the design compiler that will perform the logic synthesis to convert the RTL into a gate level netlist, and also it will provide information about the fan out of each net in the design. So after that, we will choose the higher fan out nets and find the input patterns corresponding to those nets by setting them 1 or 0 by the use of Synopsys Tetramax ATPG tool. The pattern generated then undergoes compaction with the help of a Python code. Synopsys VCS tool is used to convert the VCD file, which is generated by the Cadence NCSym, into a SAIF file that contains the switching information. Also, it is used for the gate level simulation corresponding to the patterns generated. Based on the SAIF file generated by the Synopsys VCS, the power compiler takes this SAIF file and generates the power reports, and which we can compare with our traditional coverage-driven flow. So here this graph shows the results of our proposed flow with the traditional coverage-driven flow, and as indicated by the blue bar graph, in comparison with the red one, the peak power can be better estimated using the proposed flow in all the examples we have used. So even though the functional coverage is a measure of the exhaustiveness of a design being captured by the input stimulus, we can conclude that the peak power can be estimated even at a lower coverage by maintaining the activity at the heuristically generated fan-out nets. Thus, in comparison to coverage, the activity of a larger fan-out nets is a better metric to benchmark the peak power of the digital circuits. So that's all from our side. Thank you so much for your time.